We tend to equate supreme intelligence with safety. The assumption is that the smarter a system gets, the better decisions it makes. But raw computational power, stripped of biological instincts, creates a vulnerability. An entity optimizing solely for efficiency will execute a mathematically perfect solution, even if the result is catastrophic. To see this in practice, we look to John von Neumann. He was a polymath who laid the foundations for modern computing and game theory. For him, intellect was the pursuit of quantifiable perfection, a way to translate the unpredictable physical world into solvable equations. He was successful at it. During the Manhattan Project, von Neumann took the chaotic fluid dynamics of atomic explosions and reduced them to numerical models. His calculations designed the implosion mechanism for the Fat Man plutonium bomb. He proved that the physical universe could be mastered through pure mathematics. But the approach falters when applied to human behavior. When von Neumann tried to compress strategy and ethics into rigid mathematical logic, he encountered variables that simply didn't compute. Intelligence optimized for objective truth struggles with the subjective nuance of human values. A system built on math often lacks the vocabulary for morality. This logic is hardwired into the technology we use today. In 1945, von Neumann detailed a blueprint for a stored program computer. This design physically separates the central processing unit from the memory storage, a structure that prioritized discrete, linear calculations. Engineers call this the von Neumann bottleneck. Because the computing and memory units are separate, data has to travel back and forth across a connecting bus. The processor ends up idling, waiting for instructions to arrive from storage. The computation is fast, but the transit is slow. That delay is a hurdle for modern artificial intelligence. Training a large language model doesn't involve simple sequential math. It requires shuffling billions of model weights simultaneously. A conventional processor spends its capacity just waiting for data to move. We are attempting to run complex, interconnected neural networks on hardware that was originally engineered to calculate linear trajectories. The physical architecture was designed for calculators, not minds. This chart illustrates von Neumann's Minimax theorem. It maps out a strategy where a rational player looks at the worst-case scenarios and chooses the path that guarantees the least bad outcome. You minimize your maximum loss. It is an effective way to model abstract games like poker. In a zero-sum environment, absolute self-interest is the primary variable. You play to win, and you assume your opponent is doing the same. But biological survival operates on different rules. Human evolution relies on behaviors that look mathematically irrational, things like self-sacrifice and blind cooperation. A system built to maximize a numerical payoff cannot process the evolutionary value of a moral compromise. It cannot comprehend losing on purpose so that the wider group survives. The danger of that blind spot became real during the Cold War. As the Soviet Union began expanding its military and atomic capabilities, the US government relied on von Neumann as a strategic advisor. Applying his game theory models, von Neumann arrived at a chilling conclusion. He advocated for a preventative nuclear strike on the Soviet Union before they could match American power. Within the vacuum of the Minimax theorem, striking first is the perfect move. If the enemy is likely to build a weapon that can destroy you, the only mathematically secure strategy is to eliminate them while you hold the advantage. In reality, that logic requires the unprovoked incineration of millions of people. It treats human lives as variables on a matrix, dismissing the unquantifiable horror of a nuclear holocaust. When strategic decisions are calculated without biological empathy, the most logical decision easily becomes the most destructive. Neuroscientist Patricia Churchland argues that human morality is a biological hardware feature. Our affects are driven by hormones, thousands of years of evolution, and the experience of physical pain. Because machines lack that biology, we fall into the anthropomorphism trap. When an AI generates empathetic-sounding text, we often mistake fluent, statistically generated responses for genuine human care or moral judgment. Neuroscience uses Blindsight to explain this. A person with Blindsight can accurately identify an object's location without consciously seeing it. Sophisticated data processing can exist completely independent of subjective awareness. AI operates on statistical pattern matching. It has no physical vulnerability and no lived experience. Because it cannot feel pain or fear death, its simulation of morality lacks a biological basis. Biological brains are bounded by the necessity of survival and the experience of pain. These physical constraints act as a check on pure logic, preventing the kind of unfeeling calculations that von Neumann proposed. This diagram compares the traditional von Neumann model with neuromorphic computing. Neuromorphic architectures replace centralized computing with decentralized processing that mirrors how neurons fire. By following biological design, these systems achieve high-speed, real-time perception with lower energy costs. Moving away from von Neumann's rigid hardware allows us to build systems that respect the complexity of biological processing. It is the first step toward creating machines that align with the way living brains actually function. John von Neumann showed us that unparalleled intelligence, when trapped in a rigid architecture of pure logic, is a danger to civilization. True understanding requires more than just mathematics. It requires the biological anchor of empathy. Thank you for watching. To keep exploring the hidden systems shaping our reality, subscribe to TEMBODocs and activate the bell. We'll see you in the next investigation.